Hi, I'm Madison. I am the AI Content and Video Strategist at Tomorrow.io, and you're joining us for our second episode of the Expert Forecast with Ryan Honeyager. Ryan, would you like to introduce yourself?
Hi, everyone. I'm Ryan Honeyager, and I'm leading our data assimilation and numerical modeling activities over at the Tomorrow Company.
Great. Well, thank you so much for joining us today. We'll just be starting off with a couple of questions, understanding your role at Tomorrow and what the impact is overall on the entire organization. So, thank you for joining us today. So, the first question I have for you is, how would you explain your job to someone with no background in weather or science?
All right, so I'm very heavily involved in the numerical modeling community. So, what that means in terms of everyday people is say that everyone knows how a weather forecast works in a sense. You open up your phone and you take a look, and you can see, okay, in my location or in this other city, it's going to be like 75 degrees today, and it's going to be a low of like 50 at night.
Yeah.
So with that, there's a whole bunch of complicated science that goes on with a numerical model or a forecast model. And what that model does is it takes some initial guesses to the Earth's atmosphere and it moves it forward in time. So what it does is it takes clouds, it precipitates the clouds. It assumes that the sun is heating certain bits of the air, or the parts of the Earth that's sunlit, and it just moves that forward in time. But then with these models, they eventually diverge from reality. So I'm
Mhm.
assuming for the audience, you've all heard of the butterfly effect. So the atmosphere is chaotic. A very small change or small error propagates, and it gets worse and worse and worse. So you need some way to take that model and bring it back to reality, and that's what I do. So I handle data assimilation, so taking observations from satellites, from aircraft, from the ground, and integrating that back into the model to keep it in line.
Wow, really cool. Thank you for explaining that. And I also like how you connect it to the butterfly effect. I think that gives a better understanding of what you do and how much you have to piece together because if one thing changes, then everything has to change and how you interpret the data, which is awesome. Thank you. So my second question would be, what problem are you ultimately trying to solve and why does it matter to someone watching the evening weather report?
All right, so here tomorrow, we realized fairly early on that the existing observation networks, basically providing the observations to update that model, aren't meeting everybody's needs.
Hmm.
So, for the first reason, we can say spatial coverage. So, if you care about precipitation, which a lot of people around the world care about, that's really measured only by rain gauges and by ground based radars and a few other instruments.
Hmm.
Radar coverage and the rain gauge coverage, that's very sporadic over most of the Earth. You don't really have frequent enough observations to properly constrain those models. So what they do is they fill in either climatology, so an average of what they've seen before, or a guess as to what's going on, but it's not actually physical. So without that, then you are just you have a lot of potential for error.
Yes.
So
Well, it's
yeah,
like you're like, "It's gonna rain today," and then it doesn't rain.
yeah,
That
even it
often
doesn't.
happens.
Yeah,
Yeah, and I feel like in certain, places I've lived, it's like, "Yeah, I can't really trust the weather." It, might rain, so I'll throw my rain jacket in my bag, but I doubt it, while other places is incredibly accurate. So that's
right.
interesting that your tomorrow is helping fill that gap if I'm.
Yeah, so what we're trying to do with that gap is we realized that fairly early on. So we've started launching our own network of microwave satellites. So
Mhm.
they're satellites that look at the atmosphere and they're orbiting the Earth. So they're seeing all different parts of the Earth. And with enough satellites, you get a very up to date, accurate view of what's going on. You can do that for precipitation, you can do it for temperature, just profiles of water vapor, or the audience, you might understand that more as humidity as you go
Mhm.
further up in the atmosphere. And you can use that to get better initial conditions for a better guess.
Yeah, awesome. How does knowing a satellite's impact before it launches help communities become more resilient to extreme weather? And how do you simulate that? Because I know you're talking about right, we have more data. We have specific microwave sounders that
Mhm.
are able to collect unique data that other weather companies do not have and gives it better accuracy. But when we launch them, how does that help other communities prepare for extreme weather? And how do we simulate that?
All right, so that's a little bit of a two-parter here. So the first one is by launching these instruments, you can look at storms as they develop throughout time. And everybody likes to use the common example of hurricanes and hurricane forecasting.
Yeah.
If you can see hurricane development more, you can get a better representation of the track and you can get a better representation of the intensity of the storm.
Mhm.
It's not just hurricanes. Those are always just the extreme event that everybody goes to. But for just regular thunderstorm development just outside of your community, that affects you too. Lightning matters. You want to close sports stadiums and you don't want
Yes.
kids out in fields. If it matters for transportation, you don't want to send trucks down an area where you're going to have hail.
Yes.
So, yes, by having this, you're able to make better approximations of the future, of course. But
Yeah.
to prepare too, that's its own fascinating branch of science. So, you want to prepare to figure out what your instrument's going to see before you build and launch it, because
Mhm.
otherwise, you've spent a lot of money on something that you're not sure if it's going to work or not.
Yeah.
Yeah. Yeah. So, for that, we run a set of very sophisticated numerical modeling experiments. So, to explain, let's say that you have your existing weather model on the Earth.
Mhm.
So, you get in your observations, you update the model, it makes a forecast, you get some more observations, you update the model, and so on.
Mhm.
So, what happens if you take a model and if you let it just freely run? It completely diverges, it starts making up its own weather phenomena, but
Mhm.
inside that model, you already have knowledge of what the exact temperature is, what the exact humidity is at every point on the globe.
Okay.
So you can use that as a baseline, and you can use it in experiments. So you can take that as truth effectively. And then you can run a set of experiments where you use that truth and you simulate every potential observer of the Earth's atmosphere. So a whole bunch of government satellites, a whole bunch of private aircraft, and you can simulate the tomorrow satellites on top of that. And you can run like a twin study style experiment where you say, okay, say that we start with the model initial state and say
Mhm.
that we try and assimilate those observations and then let it propagate, make a new forecast with the errors, propagate a little bit. Say that you do that with everybody's observations besides for ours, and then say that you do it in another case with our observations added on. You can say back to your ground truth how far away those observations or how far away those experiments diverged.
Oh, cool.
So you can tell, are you improving before you launch?
Yes. I actually really liked how you compared it to twin studies. I say psychology, and that's the biggest way we understand difference, right? Is by comparing the two, you're able to see the
Mhm.
distinguishing of the data. So I think that's a great way to kind of explain how we're able to simulate and how tomorrow does that is there are satellites that are, going down and collecting the data too, but how do we compare and what are we collecting? That's a great way to think about it. Okay, next question. So thank you for answering that. And it was a big, lots of things to answer in that one. In plain English, what's the difference between an observation simulation system experiment or an OSSE and an observation system experiment OSE? And why do they matter for forecasting?
All right. I will apologize for the field because we have some very technical, long-winded terms that we just always turn into acronyms. So yeah,
Yeah.
that first one, we call it an Aussie.
Oh, an
And
Aussie.
it's
Okay.
hard if people don't pay attention to the pronunciation because the other one's just an OSE. But
Okay.
yeah,
Okay.
the last one.
They look very similar and sound very similar, but I'm glad I know the technical terms. I appreciate that.
Yeah, so the first one, the observation system simulation experiment, is what I just described. You basically are running this entirely in computer space. So you have your truth, that's just this free running nature run of an atmospheric model. You
Mhm,
have your twin study, you know exactly what you're going to see. But that has some error associated along with it, because even the best numerical models don't capture all the features that we see in the Earth's atmosphere. The model itself might not convect a cloud properly. It is subject to all these biases because a human wrote that and they tried to break down the equations of physics into something that we can understand and
mhm.
something that we can put it maybe on like a model grid. Think of it as like a map, like a Cartesian coordinate map or like just a standard lat long grid.
Yeah.
And yeah, that adds on its own bias. You also have some bias in how you would just convert that model representation of reality into what the instrument would see. So there's all these different potential errors. So it's good for preparation, but it's not like the gold standard for showing that you're going to have impact. It just leads you along the right direction.
Okay.
And that brings me to the other style of experiments, and these are the observing system experiments. And the
Okay.
difference is that these are done with real data.
Okay.
So it's done with real Earth observations. You can only really test once you've actually launched your instrument into space. And it's nice that we've launched a couple of satellites now, so we can start running these experiments.
Mhm,
The downside for those is you no longer have an exact knowledge of what was going on in the Earth at any given location or at any given time.
mhm.
In general, you also get the entire wide range of the Earth's weather, so it's really a proving ground. And that's like one step away from what's used as an operational model. So
Okay.
these observing system experiments, they're typically run on the same platforms using the same code as to what is used in production. So it will show
Okay.
you exactly what impact you're getting.
Cool. Thank you. That's really interesting. Those are like very significantly different, even though they have very similar acronyms. Cool. All right. Well, the next question then would be, what is the JEDI infrastructure and how does it help you improve forecast? And hopefully I pronounced that right, or
You're
I'm wrong. I read it as like Star Wars, like Jedi, but it also might just be JEDI.
okay, so I'm a big fan. I'm actually wearing a Jedi themed shirt right now.
Oh my gosh, love
This
it.
on camera. Yeah, it's got all the different TIE fighters and Star Destroyers on it. But
Cool.
yeah. So JEDI stands for the Joint Effort for Data Assimilation Integration. Assimilation got left off from the acronym because Jedi just sounded cooler, but it's
Sure.
the next generation framework for doing data assimilation experiments and actually using it in operations. So, what I mean by framework is that it's shared code that's in development by a whole bunch of different federal and international agencies. So, NOAA works on JEDI, NASA works on JEDI, the
Okay.
UK Met Office works on JEDI, the National Center for Atmospheric Research. We contribute a little bit to this, and it's designed to represent the future.
Okay.
So, with as part of a little bit of history, whenever a different forecasting center wanted to perform data or conduct data assimilation experiments, what they had to do is they had to build their own system from scratch. And you have different scientists with different levels of expertise in different domains.
Hmm.
Because, yeah, sure, it might seem like meteorology is one big unified field, but the more you look at it, the more you realize there's all the sorts of different disciplines.
Okay.
So a center might be very skillful in one area and not another.
Okay.
Also, if you wanted to just take a new instrument and add it on to this forecasting model, you would have to do this independently at every different center. And you had completely different code bases written in completely different languages, some of them really, really old, and you'd have to engage an expert to actually figure out how to write everything. And it
Yeah.
just took forever. So JEDI is an advancement on that. So it's going to
Okay.
power the next generation forecast systems starting, I think, this year with the UK Met Office and with NOAA for some of their forecast components. And it's rolling out right now. It's really great and easy to use. I'm definitely a fan.
Cool.
Yeah, so I'm using in my experiments to basically avoid all those coding issues that I just brought up. I can write science and configurations for our instruments instead of writing raw Fortran or C++ or Python code.
Okay.
So that's the real benefit. I can share that with any of our partners besides just using it internally, and they can just say, okay, we can integrate this instrument really fast now. We
Hmm.
can also, okay, we can integrate this instrument, the best science that's available, say at the UK Met Office for observation, processing, and quality control. Combine it, well, yeah, that's JEDI.
Yeah. I like it, and I feel like it's also symbolic because I mean, I'm not like I don't know everything about Star Wars, but it sounds, like Jedis are the good guys, and they're like they want the universe to be like, united, and I think that's cool that it also represents, everyone coming together using the same thing, kind of like dissolving the division so that everyone is like actually producing like right the best data, the best science and weather, which is very cool. So I like the name. I like what it means. Very
Mhm.
cool, and I like your shirt.
Okay.
Um, so I'm going to move on now because I want to zoom in on a little bit on satellites and forecasting in more detail. I know we just kind of went over a lot, but I want to get even more nitty gritty. So then my next question would be: when one of Tomorrow IO's satellite launches, what kind of data are you most excited to get, and what do you do with it?
All right. So my group is one of the very first groups to see the data from a new satellite. And that part's really fun because it's like, yeah, you get to like open up like a little box and pull out the files and just see like, oh look, nobody else has seen this before.
That's cool.
Yes. So that also means that I get to look at the satellite data at a fairly low level. So I see some of the initial data products that we produce, which are proxies or like 2 or 3 steps away from the actual raw instrument counts that the sensor is seeing and broadcasting down to the ground. They
Hmm.
go little bit of calibration from a group upstream of me just to make sure that they're all standardized and that any like obvious biases are corrected for and to make sure that the instrument is working properly.
Yeah.
And then I get that nice view. So I get to view raw satellite radiances. Think of our satellite instruments as cameras in space.
Okay.
Okay, so our eyes also act as cameras. We just see
Mhm.
red, green, and blue. So we have like the different rods and cones in our eyes. For a
Mhm.
satellite, it has something this similar, but instead of seeing red, green, and blue, it's looking at different microwave frequencies.
Okay.
And our satellite can see like 12 different bands of radiation.
That's really
Think of
cool.
it like 12 colors.
Yeah, that's
Yeah,
awesome. That's
yeah,
really cool. And then
yeah.
you're interpreting that
Mhm.
those directly from it.
Yeah, definitely. So basically, the low level data, it's incredibly useful. So I work in data assimilation. So I take that data and I also can see what the model should be seeing at about this particular time. And I can link the two up through what's called an observation operator. So it takes model fields and it turns them into observations.
Okay.
So what it does is it takes what the model is predicting in terms of temperature or like surface wind speed or other parameters, and it converts it into something that it thinks that the satellite should be seeing at each of those different channels.
Okay.
Mhm. It also provides the logic to go backwards. So I can take what the satellite is seeing and say, how should I adjust the model?
Oh,
So
interesting.
that's the level at which I'm doing this type of work. And yeah, that's the first thing that I do. I make sure that that is working consistently. And then I refine the science or the algorithm to do that. And then I get to actually run those OSE style experiments that I was mentioning before.
Oh, wow.
Basically to like do the first set of checks, refine the model a little bit, and
Yeah.
then say, okay, now let's run it over a month and let's see, is it having the impact that we think it would?
Wow, very cool. And it's very cool that you're like your team just gets to like get the data, the raw, like basically the raw data. You said this is the team that slightly goes in, makes sure there's no major biases or errors, but then you get to go take it and basically you're the one who makes it into models, which is awesome. Okay, so my next question then would be, how do these experiments improve the weather forecast people see in an app or on a dashboard? So when I open up my Tomorrow weather app or my normal weather app on my phone, how does it impact it?
Okay, so for our observations, one of the benefits to having a different satellite constellation compared to what's up there already is we can play around and launch many more satellites than what are available in space right now, and they can see different parameters. So, with having more satellites, we have a better revisit rate and a lower age of data over any point on the Earth than what you can get with just the standard government style constellation. So that affects your weather app first for the very near term. So for nowcasting, what are you seeing now? Is there a storm nearby and how will it evolve throughout time? If you
Mhm.
have more recent observations, you can feed in better data into a model because the model is really constrained by those observations more than anything
Yeah.
else. It might have the best physics in the world, but if you have a chaotic process like storm development in an atmosphere, storm might be in one spot or it might be like 5 kilometers away. And without the observation, you can't tell where that's going to happen.
Mhm.
So that's the first thing. And then on the longer time scales, by doing data assimilation, by just tweaking those initial conditions that you're feeding into this forecasting loop, you get better conditions down the road. So small
Mm.
changes now amplify and produce larger changes later. So by launching more microwave sounding satellites, you get better temperature and cloud development forecasts around the world on the scale of 6 hours through 4 days and beyond.
Great. That's so cool. I think how I think about it too, just because I'm like in my AI brain is, oftentimes when we're teaching new people how to use AI, it's very smart, but it's also only smart with what you give it.
Yes.
And it has to learn. So the more data and more powerful the data, and we're an AI company ourselves too,
Mhm.
um, the better it performs, the more accurate the output's going to be. And the more we launch our satellites, the more data we collect, the more accurate the weather forecast is. You can have, like you said, the best physics, the best science behind it. But if you don't have the right data, it's not going to be accurate. And it can be like what I get on my phone sometimes where I'm like, don't know if it's actually going to rain, but we'll see.
Yeah, it works like that most of the time. I mean, sometimes you can provide so much data that you flood the model, so
Mm,
it doesn't know how to do with it all, or it might be too computationally challenging. There's ways to work around that also, but in general, there's these big observing system gaps of several hours between satellites passing over a certain spot. If you
Oh,
can fix
wow.
it and make it like even hourly or every 30 minutes, you're pretty good.
Yeah, I mean, closes the gap.
Yeah.
Cool. So my next question would be, can you give an example where assimilating real satellite data made a noticeable difference in forecasting accuracy?
Oh, there's
I'm
so
like,
many of those. That's an easy one. So,
okay.
I mentioned hurricanes. Hurricanes are always the go-to for anybody in NOAA when they say, okay, does a satellite matter or not? It helps you improve the track forecast. It helps you improve the intensity forecast because you're just providing more observations. The same
Mhm.
applies even on mesoscales for tornadoes. You might not be exactly sure where you're going to get a tornado in a rotating storm. But really, with frequent satellite observations to supplement radars, you can see that development much more clearly, especially if you're in an area where you don't really have good radar coverage. It might be
Yeah,
something due to the terrain, or the radar just might be down at the moment. So there's that. You have cases where satellites help you improve forecasts for features like atmospheric rivers or fronts, where you
yeah,
have a lot of precipitation falling on an area in a very short time. So for fronts, I mean snowstorms, or anybody off in the Northeast knows
yeah.
sometimes you get a snowmageddon, and yeah, it's, sometimes it's the difference between forecasting 1 inch versus 2 feet.
Yeah, that's a huge deal. I mean, it affects so many people. It affects think about tornadoes or even again, a massive snowstorm. It could affect lives. It could you think
Hmm.
about those crazy storms that happen in Texas, right? No one ever has experienced snow before. It's like having real impactful weather data can make a huge difference of how people prepare.
Yeah, it even goes on to the smaller scales too. So, like for airlines, over tomorrow, we can tell airlines where and when they should start de-icing their planes for certain routes.
Wow.
So, yeah, it's public safety just on areas where nobody even is aware of it or pays attention.
Yeah, it's super important. So
Yeah,
important, right? You don't wanna hop on a plane that is not safe for liftoff, right? I
yeah,
don't think
exactly.
anyone wants that. So in expanding, which is kind of what I we were talking about more on public safety side. Beyond public safety, how does technology help businesses? So I know you mentioned airlines. I think you kind of briefly mentioned trains, but is there another maybe industry that people wouldn't expect that this helps?
So I'll start a bit more generally. So we like to produce forecasts in a form that people can use.
Mhm.
So if you run a numerical weather model, you get a lot of data, gigabytes and gigabytes for your region or your globe. It's very dense and you have a lot of raw information, but you don't
Mhm.
have the ability to really understand that information unless you're a specialist and
Yes.
unless you have like dedicated plotting tools and
Mhm.
whatnot. Say that you manage a sports stadium. You don't care about any of that. You just want a nice, easy report saying, okay, at around this time to this time, you might have to delay your game due to excessive heat
Yeah.
or excessive wind or excessive precipitation. If you are running a sports network, you might want to say, okay, we might have to change our schedule to optimize our broadcast time to always have a game that's actually playing instead of just being stuck with the delay of game.
Mhm.
Yes, it's the same for transportation. You want to be able to have trucks and trains get routed on tracks that are safe to use, as opposed to ones where there might be excessive winds for derailment or turning the vehicle
Yeah.
over, hailstorm. Yes, so that's what we're trying to specialize in, and that's the impact besides like those bigger public impact events, just on the
Yeah.
day-to-day business operations just throughout the world.
Yeah. No, it's so important. I don't know even before I started tomorrow, I understood how much weather impacts so many different industries, and it's so important that we're prepared. Um, okay, great. Well, moving on to our final section. Oh no, our final-ish section of questions. Um, I want to pivot to kind of about purposeful innovation and your specific industry perspective.
Mhm.
Um, so I want to ask you, how is tomorrow taking a different path from the rest of the industry with this approach?
Well, we kind of led the industry in a lot of all this work for making a weather platform. We were pretty much the first on the market for all of this, with realizing that there was a business need in addition to just the standard, oh, you look at your phone and here's maybe a little weather report for your particular city.
Yeah.
So, yeah, the pathing, the integration. And then we were some of the earlier ones to realize and do in house, or realize that you are limited over wide markets or regions of the globe in terms of the data that you have, and we
Mhm.
actually proposed a solution for it. Satellites weren't actually our first solution, but it was the first one that we thought was feasible,
Yeah.
and we're exploring several different technologies for this. So right now, often our press releases, we're really talking about our sounder constellation, and those who are the ones that are launching most recently. We're
Mhm.
also exploring radar technologies too, and no one else is looking at those. And that will give us an even better view as to the precipitation dynamics within a cloud, and will really help us on our regional forecasts with just even further moving the field ahead with being able to make an accurate prediction. And
Cool.
we'll continue to innovate on areas like that, and with any luck, we'll be able to transfer that into our models pretty soon and just still keep on raising the bar.
Yeah, I feel like we're constantly raising the bar. Like it's
Yeah.
like there's always a launch, there's always something new happening. It's very exciting in terms of like how much we do in terms of the back end of our satellites and all of the science that goes behind it. It's very exciting. Um, so my next question for you would be, what are the biggest challenges in getting satellite data into weather models, and how are we overcoming them?
All right. So it is a challenge to build and launch all of these satellites. And I'd say the big challenge is being able to improve on the existing observing system. So it's not as if governments and have it's not as if governments have just sort of sat doing nothing. They've launched a whole series of instruments designed to look at the Earth. So you can get that data freely. It's very well documented, it's very well calibrated. These are very large, many billions of dollars missions where they launch them every few years, and it just provides a tech demo of what was possible. And
Mhm.
you can just look at the Earth in visible light and infrared and microwave. You can tie it into models in a whole bunch of different ways. So
Yeah.
that already sets a challenge to overcome, because just by launching a satellite, well, that doesn't mean much. You have to launch a good satellite, something that looks at the atmosphere more accurately than before, or looks in an area nobody else is looking at.
Yeah.
So, yes, so I'd say the challenge there is figuring out what the gaps are, and
Mhm.
figuring out how do you build the instrument that's a lot smaller, a lot lighter, maybe a lot less expensive because technology has advanced, and have it make a good contribution. So, I mean, that's why we do my sort of research, doing those before launch studies, making sure that the instrument is calibrated very well, just having debates over which channels to look at or which parts of the electromagnetic spectrum are valuable for us or not.
Mhm.
Yes, that takes a long time to transition from research to operations.
Yeah.
The technical readiness levels, at least they've steadily increased, and we're able to do a lot of very good stuff there. But
Yeah.
it's going to remain a challenge.
Yeah, and it's funny that you say it does take a lot of time, and I remember when I was talking in our last expert forecast that, to Jack that, we are relatively fast, and it
Mhm,
still takes, like, 3 years for really for a launch to happen, for these innovations behind a new satellite or a sounder to happen, and to me, I'm like, "Whoa, 3 years, it's so long," but that's actually way quicker than the industry standard. But we're always innovating, and it's like in the back end between every launch, there's so much happening for the next launch and innovation between all those, that I only get to maybe talk about it in these type of conversations and learn about, which I always really enjoy. But also, followers of Tomorrow IO also kind of just see the final goal and don't understand all the challenges and all the tweaks that have to be made
mhm,
constantly over years and years
mhm.
to get where we are.
We're lucky that there are a bunch of technologies just waiting to be brought up to space where they've finished the airborne campaigns, they've finished the development, and we're lucky too in that we're able to assembly line a lot of different satellites together.
Yeah.
Just having one precious satellite that may launch once every 10 years, yes, we're definitely benefiting from that.
Yeah.
But, it's really nice to be able to just take some of these cool technologies and put them up into space.
Yeah, we're very lucky. It's so cool. Okay, and I have two wrapping up questions about kind of looking forward. Um,
Okay.
so my first one will be, what excites you the most about the next generation of weather satellites, or the next big advance in your numerical modeling, and what's the impacts it'll have on forecasting?
So I'd say the next advancement, well, we're at the forefront of advancing right now in producing a proliferated low Earth orbit constellation, which is to say that we will take global revisits and bring them down to being sub-hourly for microwave observations.
Mhm.
So that's one. The next step will be to start looking at instruments that go beyond the standard microwave sounder paradigm. So
Mhm.
there are visible and infrared instruments already on orbit, but there's a whole bunch of other categories where we could explore. I'm
Mhm.
personally a fan of our microwave radar program. We flew two Pathfinder or proof of concept satellites a couple of years ago, and
Mhm.
one I think has just completed its primary mission, and the second one is about a year out. But
Okay.
we collected a lot of very valuable data, and we'd like to take our tracker program and make it an operational reality. So just deploy those everywhere for atmospheric Ka band radar. So that will give us really good understanding of cloud fields. And then there's all these other new future technologies, from surface pressure sensing radars to ones that can give you wind fields to all sorts of observations that people could only dream of just even like 20 years ago.
Yeah.
Yeah.
It's
So
crazy,
it's
like, how much
exciting.
tech progresses, like, it's just I feel like it's quicker and quicker, and I bet it's really exciting to be in a field that has so much innovation and is constantly morphing, and you get to be like,
Mhm.
again, tomorrow is a leader, and you get to be at the forefront of those technologies, of those changes, so super cool, and I like to hear what you were excited about, that was really interesting as well. And then my final question, we're almost at the end.
Okay.
Woo! Is for young people inspired by this work, what skills should they start building today?
All right. So, if you're inspired by this, there's a whole bunch of different ways in which you can contribute or where you can pick this as a career path. So, for the most basic level, just the raw engineering and science and math skills to understand what's going on, to
Mhm,
understand the design, to understand the physical concepts behind what's being done and why it's being done.
mhm,
That's essential. On top of that, it really helps if you have a knowledge of programming languages, or if you're able to order your thoughts in such a way that you can take those ideas and turn them into something that a satellite can use. It's
mhm.
not like there's like a person up in space, like jotting down the observations.
Yeah,
You have all these cool algorithms with very, very fine tolerances to make everything work very well.
mhm,
Third thing that people need nowadays is some knowledge or background in artificial intelligence and machine learning.
mhm,
So that's a whole class of algorithms that can be developed that really let you just advance even faster than before. And they can infer lots of cool stuff from your observations that would normally take a person years and years to produce an algorithm to retrieve.
mhm. Yeah. Well, cool. I think, hopefully that advice is taken and we have some, future, data assimilation scientists, that wanna join tomorrow down the line because I think we'll just keep on innovating and innovating. With that, if there's anything else that you'd like to say or ask or tell to the people, the floor is yours, but if not, this is the end of our, second episode of the Expert Forecast.
Well, I don't really have too much to say past this, but I'll say, yeah, Madison, it's been fun. And yeah, I'd love to see how this whole program goes.
Yeah, me too. I look forward to more Expert Forecast interviews. Thank you for your time. I really appreciate it, Ryan.